So for the past couple of weeks, we've been observing a star called Lo Pegasi, and this star has dark star spots on its surface, which are basically analogous to sunspots. And as the star spots rotate into our field of view, the overall brightness of the star diminishes, like as if they're pointing away from us. The brightness of the star is heightened. So basically, star spots are the same things as sunspots. They usually have a dark central region called an umbra and a lighter outer region called penumbra, and on the sun they're surrounded by convecting cells of plasma called granules.
And I'll be explaining why the sunspot looks darker, and basically one thing to note is the sunspot's cooler, and that's because of high magnetic fields passing through that area, like as it shows in this picture. And basically the physics behind this comes from Faraday's law and Ohm's law, which I won't go into detail, but the basic approach is that the outer side of the star is the convective zone, and basically the area where there's strong magnetic field penetrating, the convective zone is inhibited, or the convection cycle is inhibited, causing a less efficient heat transfer there, causing that area to effectively cool down. And also it looks a lot darker than the photosphere itself. That's because of Stefan Boltzmann, that is, the intensity has a force power dependence on temperature. So if the temperature goes down a bit, there's a bigger difference in intensity.
So we take images of our star with a telescope with a CCD camera hooked up to it, and we take images through 4 different filters. And before we can do anything with these images, we have to process them and get rid of noise. For us, noise comes in 2 different forms. First of all, vignetting, which is darkening of the image around the corners, and that happens just because of the uneven illumination of the optics of the telescope. And secondly, our form of noise is called dark current noise, which is basically thermally excited pixels. And so once we get rid of that, we get a cleaner image and less noise to work with. So then we can do differential aperture photometry, which basically will determine the relative brightness of our star based on a star with known brightness. So we use a comparison star like that because we're observing from Earth, and we have an atmosphere to look through. So from the time a star rises to the time the star sets, the brightness will fluctuate due to the atmosphere alone. When a star is directly ahead of us, we're looking through less atmosphere than we would be when the star is on the horizon. So we want to make sure that any variation in brightness of our star is due to the presence of star spots and not just due to the presence of the atmosphere. So we use that comparison star with a known constant magnitude to make sure that our variations are because of star spots.
And basically, using this light curve, we feed it through an algorithm called the matrix light inversion. And basically, it looks at the light curve and tries to reconstruct the star surface with the location of the star spots. And basically, this algorithm takes many factors into account, and one of them is limb darkening, which is basically the darkening of the edge of the star. And that is more pronounced in the different filters, and that is why we take the picture of the star with different filter, namely the infrared, blue, and red, and the visual. The other thing to note is that the algorithm that we are using is very sensitive to noise, and other algorithms are also sensitive to noise. And if we don't take care of the noise, we can get a reconstructed surface like this, which is not a very good surface reconstruction. So we use a smoothing function which causes the algorithm to have a bias towards what favors darker spots and overall smoother surface. So after we feed it to the algorithm, this is the results that we got from the past year, and the one that we did this year was this one. And as you can see, the star spots have evolved over time as it starts to split into 2. And the other thing that we found is that the period of the star is not, it's changed. It's not 10.17, it's 10.153, as we can see over here. Mind you, that's only 1 minute difference, but it does add up as we have observed the star over weeks.